Hello everyone, welcome back to Historical Geology 1404. Would you grab the door for me, someone? Come on now. There it is. Today is lecture 4. It is our discussion about sedimentary environments, and you are getting lab 2. How are we doing on lab 1, by the way? Pretty straightforward? Great, great. This is what I love to see. It's all review, basically, right? You should be old hat at this sort of thing. So good. I'm glad to hear so many of you are finished. If you're not, try and finish it up today so you can get started on lab 2. Lab 2 is going to be a new concept using old ideas. Okay? So we're building on top of the foundation that we got in 1403. Excuse me, I forgot to bring my water bottle in here. Let's see. This is the last lecture of Module 1. When we meet again next week, we will have an exam review session. I always give you guys an exam review session before exams. Even though this is mostly review, I still want you to be prepared as possible for your first exam. Okay? So then your exam is going to be open. Let's see, I'm going to open it after class on Tuesday, and it will close before class on Thursday. Okay? So you'll have that 2-day period to take the exam. All right? And this is true for my online students as well. Make sure you abide by that window. Let's see, what else? I think that's probably all I've got for class announcements. Any questions or comments or cool stories that you heard? No? Everyone doing all right? Ready for another week? I loved how chilly it's been the last couple of mornings. And this morning it wasn't that chilly. And I was like, man. Like the chili. All right. Well, let's jump into the content. Today we're talking about sedimentary environments. Remember, a sedimentary environment is more or less, you can think of it as a clue to the past preserved in sedimentary rock. What do I mean by that? Well, our Earth is covered in many different types of environments. Name some of the environments we've learned about. Deserts. Glacial environments. Dry, we can kind of aridity, right, is kind of broadly categorized into that desert, so we just heard. What else? Shoreline. Okay, shorelines, great. Oceans. Mountains. Huh? I heard someone else say something. After mountains, I thought I heard someone say something. Earth's surface is where these environments take place, right? Any other ideas for environments over here? What was it? Valleys, sure, yeah, valleys, basins. Caves. We already heard deserts, but good. Marine, I already heard ocean, but yes, good. Okay, so we've come up with 7 or 8 different environments here just now, okay? And there are definitely more, but I'm glad that you all were able to come up with that many. Fantastic, okay? Now, each one of those environments exists right now in the world somewhere. And as it is existing there, sediment is being deposited in that place in a unique way, preserving unique characteristics that come from that environment, that will only form in that environment, okay? Now, the principle of uniformitarianism states that if we are observing these processes being preserved in the sediment right now, the same thing must have happened in the past, right? So using that concept, we can go through sedimentary rock, find evidence of those environments that is exactly like the evidence of the ones that we see existing right now, and make interpretations of the past by studying what is occurring right now. Okay? So what you see here, these are just a few examples of sedimentary environments that we can observe and then interpret to make a conclusion about Earth's past. All right. Included in these environments are many of the ones you just talked about. Ocean basins, deltas, lagoons, soils, lakes, glaciers, deserts, all of that. These are all environments that we have talked about in the past and which we will talk about again today, except in a little bit more detail as far as what it comes to interpreting that data. Not just the existence of it, but how we interpret that. Okay? We're going to start with marine sediments and marine sedimentary structures. Okay, so remember that means bottom of the ocean stuff. Okay? So, out in the ocean basin, it is very common that the sediment which settles to the bottom is extremely fine grained. Do you remember what we call the sediment sizes that are that small? Hey, he lives! All right, what do we call the sediment size that is really, really, really small? Huh? I mean, they're all grains. Sediments are grains, but what do we call the sizes that are so small that they really only filter down to the bottom in extremely low energy environments? The grain sizes. Yes, they are small particles, but there's a name for those particles. There's actually two. Huh? Detrital. They are detrital particles, but there are names for these sizes. I'll give you a hint. One of them is silt, and then there's a smaller one. Huh? No. The smallest, yeah? Very fine, which is, there's a name for it. There's a name for it. It rhymes with play. Clay, right? Remember the far end, the small end of our sedimentary grains sizes chart? There was silt, and then there was clay, right? Both of those are the smallest. Clay being the even smaller than silt, right? So when we're talking about deep ocean basins where energy is practically non-existent in the water, it barely ever moves, that's where our fine grains, our silts and clays are going to filter down to the bottom, but they're not the only thing, okay? The living microscopic organisms in the water column are going to live, they're going to die, and as they die, they also filter down to the bottom of the ocean through this low energy environment. And so what we end up with is a collection of a lot of little microscopic dead bodies, okay? The planktons and zooplanktons, foraminiferans, coccolithophores, radiolarians, all of these things, okay? They collect there at the bottom of the ocean along with the clay and the silt. And depending on what those shells are made out of, we will give a specific name to that, that sediment, okay? So, this pelagic sediment, as we call it, pelagic thing, when you hear pelagic, think bottom of the ocean, okay? This pelagic sediment is usually broken up into two categories, okay? You've got your, and I apologize if this word disturbs anyone, ooze, O-O-Z-E. Ooze. Well, okay, so there are some people that find certain words very disturbing, like the word moist, for example. Some people, you didn't like that, did you? Yeah. You flinched when I said it.
How do people find that?
Yeah. Well, some people can't stand that word.
Is that like
Huh?
the heat or like the temperature?
What the word is?
Yeah.
It has to do with how wet something is, okay? The level of moisture, okay? Some people also have a problem with the word ooze, okay? So, but if this sediment, this pelagic sediment is rich in calcite shells, we call it a calcareous ooze. If it is rich in silica-rich shells, we call it a siliceous ooze. Now, I gave you a clue before as to why I would have shells made out of calcite versus shells made out of silica. Can any of you, remembering what I taught you about this before, give me an interpretation based off of that? If I have calcareous ooze at the bottom of my ocean, make an interpretation. If I have siliceous ooze at the bottom of my ocean, give me an interpretation. What do you think? Bless you. Bless you again. Can any of you remember when I told you if a shell is made out of calcite versus when a shell is made out of silica, what that means, what we can interpret from that? That's okay. It's okay if you just spit it out. I don't mind. All right.
What was the question again, sir?
When I have shells made out of calcite versus shells made out of silica, what does that tell me about my water, about my environment? Say that louder. A little louder. Be victorious. You did it. It's different temperatures. Okay, yes, this is absolutely the interpretation I can make. Okay, if I have a shell made out of calcite versus a shell made out of silica, it's because of the temperature of my water. Why would that matter? You remember I told you this weird thing about calcite? It dissolves easier in what? Cold water. Most things dissolve easier in warm water. Calcite tends to dissolve easier. It becomes less stable in cold water. So, animals living in cold water cannot rely upon calcite to make a stable shell. So what do they use? They use the dissolved silica in the water around them instead of the calcite. So if I am looking at the sediment at the bottom of my ocean and I see that the composition is mostly siliceous ooze, what can I interpret? It's a cold water environment. We can see this is true today. You go up to the north or south poles and you're going to find more creatures that have silica shells than you do creatures that have calcite shells. Okay? Whereas when you go close to the equator, you're going to find the vast majority of stuff there has calcite shells versus silica shells. So if I'm looking at a rock that is the result of solidified, fossilized siliceous ooze, then I am looking at a marine environment that was cold. And I can reasonably assume it was somewhere near the equator, or one of the poles at that time. Okay? It's a clue. So we look at the environments that form today to interpret the past. Okay? Just a little evidence of that. Okay, so when this calcareous ooze gets fossilized, gets solidified, goes through lithification, it makes limestone. The calcareous ooze will make limestone. The siliceous ooze, that makes chert. Okay, chert is a result of the compaction and fusing of siliceous ooze. There are several caves that I take people into a couple of times a year, and either through limestone beds. And as you're kind of climbing down deeper and deeper through limestone beds, we will see blobs, just random blobby shapes poking out of the walls. They're a different color than the limestone. They're a little more yellow. When you tap on them, they sound like glass. It's because that they are made out of chert. Why are there these random blobs of chert? Because what we're looking at are blobs of siliceous ooze in the calcareous ooze that was there before. Because some silica organisms, shelled organisms, were starting to live in that area as temperatures cool off. I can interpret the rock hundreds of feet underground in this cave simply by knowing this concept. Okay? I can understand more about the environment that I am crawling through the evidence of that was hundreds of millions of years old. Okay? So it's pretty cool. All right. So now let's move on to the near shore environment. Close to the shore, we are going to be seeing slopes coming from the continent down into the ocean basins. More of a steep slope and then a more gentle slope the further out you get, okay? Now, the flatter, more gentle slopes, we tend to find those have some sort of undulating dune sort of shape. Very low angle, lazy looking dune shapes. Because the water is slowly moving sediment closer to land. But whenever there is some violent energy, say from a storm, we will often see sediment break off of this shelf and cascade downhill further out into the basin. We call these tempestites, or I should say, yes, tempestites is the word that we're going to stick with here, okay? So when you have a tempestite, stuff is broken off of this near shelf. Some of it may fall down the shelf a little bit further, making a landslide, but then it gets picked up by the energy of the storm and carried inland, okay? So stuff gets broken off, ripped up, and carried inland. So this is how we can end up with near shore sediment, like say a beach deposit, that has offshore chunks in it. So if I have shale being deposited offshore and sandstone being deposited on my beach, a tempestite will look like sandstone with chunks of shale in it. They look kind of weird, okay? So here we see sandstone, 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 chunks of shale, just randomly interbedded with my sandstone. And then more sandstone, sandstone, sandstone as I go up. That's a tempestite. That can only happen when an incredible amount of energy caused by a storm, hence the name tempestite, okay, brings those chunks of debris inland, okay, and intermixes them with the sand. Deltas. Remember, a delta is when I have a river system that interacts with a larger body of water, typically an ocean or a bay, like the Mississippi right here interacts with the Gulf of Mexico, okay? And when the relatively high energy river interacts with the ocean, which is relatively low energy, the energy is absorbed, it stops, and once that energy is lost, what happens to the sediment that was being carried in it? Yeah, it falls out. It deposits. And that's what builds up our delta further and further and further out. Okay? So this is kind of a side view of how deltas build out. Layer upon layer upon layer. The delta front continually pushing outward. Okay? Lagoons. A lagoon forms behind a barrier island. Recall that a barrier island forms excuse me, as storm water pushes sand from offshore and closer to the land. It piles up on itself, and the higher up it piles, the further up it piles, every successive storm building it up higher and higher and higher, you're going to form these islands parallel to your shoreline. Okay? So you're going to get a long string of islands parallel to your shoreline. We have these in the Gulf of Mexico, okay? If you've ever gone to Padre Island, okay? Any of those islands just off the coast, right there, those are all barrier islands. There's a ton of them out there, okay? And then behind them, those are lagoons. Very calm water, perfect for swimming, boating, any kind of sport you really want, okay? Excuse me. Those lagoons tend to be very interesting, unique ecosystems because as the tide comes in and out, that is more exaggerated in your lagoon than you would typically think, okay? Most of the water kind of gets sucked out between your barrier islands, leaving big expanses of shallow water or mud flats. And then the tide comes back in. So the ecosystems that live in lagoons often have to adapt to be partially or all exposed to atmosphere half of the time. Okay? We'll talk more about lagoon ecosystems further along in the class. Because it is very calm water behind that barrier island, most of the deposition that occurs there is fine-grained. Okay? Not a whole lot of wave activity makes it through there, and so you don't get a lot of energy for the larger particles to be carried in. All right, fossils. How do fossils tie into marine sedimentary structures? Well, a lot of the time is the answer there, okay? Fossils, the record of fossils on Earth is far longer in the ocean than it is on land. Life started in the ocean. We will talk all about that starting in Module 2 next week, okay? But for now, let's just say the fossil record in the ocean is extremely long. On land, far less, okay? Well, not far less. I'd say half. It's half as long, okay? No, that's not true. From single-celled organisms, from non-bacterial organisms, it's half as long, okay? Bacteria go way further back, billions of years further back. All right. Again, I'll go over all that later. Some examples of fossil systems that we can find that create their own sedimentary structures. Reef systems make their own sedimentary structures. They are a sedimentary structure after they become fossilized. Matter of fact, I believe I told you before that the entire Guadalupe mountain range is essentially one large fossil coral reef. Do you remember I mentioned that? It's huge. How many of you have ever been out to the Guadalupes? Yeah, the mountains just further west, out in New Mexico. No? No, you should go. It's great. Fantastic caves. But even if you just go like hiking, you will come across fossils all the time. It's all limestone. It's all one old coral reef. Okay? So there's another way that these can happen called an atoll. These are actually very common. An atoll, A-T-O-L-L. What happens is we get a volcano out in the ocean. It rises up through the same process that we learned how volcanoes are created, layer upon layer of lava building itself up from the bottom of the ocean, okay, until it peaks up above the ocean. Now, it's still building, but now there is land out there in the ocean that is providing a place where coral can anchor themselves close to the sunlight because they require the sun, okay, and the moon, but they require the sun for photosynthesis, okay? So you get this buildup of a reef around the perimeter of my volcano, and as my volcano dies and starts to become weathered away, it starts becoming closer to sea level, but the reef system around it, this ring of reefs, only gets larger and larger and larger. And so finally what's left is either none or a very small volcanic remnant with this big old ring of reef system around it and a lagoon in the middle. We call that an atoll. Here is a real one. This is a real picture of an atoll. This is where a volcano used to be, and it's completely gone. It kind of looks terrifying now. Yeah, exactly. It's like, man, what's in there? The volcano is way down deep under there, what's left of it. Okay? That's all reef. Okay? We actually have a fossil atoll here in Texas. Right there, not too far from us. That is one big atoll complex. Can you imagine how big that volcano must have been? Must have been a massive volcano, okay? But yeah, that is a fossilized reef complex right here in Texas, just north of us. All right. I told you a little bit about stromatolites before. Who can remember what I told you about stromatolites? Lecture 1 or lecture 2, yeah?
It was in the first lab.
Yes, it was when I talked about the first lab. So lecture 2. What are stromatolites? Does anyone remember what I said?
Isn't it like stuff drifting off the ceilings and makes like little cones go down?
That's not a stromatolite.
Wet lands that have sand and mud or silt.
Say that again?
Wet lands that have sand and mud or silt.
No. So stromatolites are fossils. Okay, so a stromatolite is a mat of algae that wants to be close to the sun because it's photosynthetic, okay? And so it's in shallow water, but as tide goes out, it's exposed, and when the tide comes back in, it puts a little layer of silt on top. And so my algae has to grow up through that layer of silt to reach the sunlight again. And this happens over and 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 over. And so eventually what I've got is, instead of this mat of algae sitting at the bottom of my lagoon, I have kind of this mound that gradually takes on a more mushroomy shape as time goes on. This mushroomy shape, we call them stromatolites. They are interlayers of algae and sediment. Okay? They are interlayered algae and sediment. These are very common in tropical oceans where you have warm, shallow seas and carbonate platforms like this. These carbonate platforms are the result of just so much life dying and piling up that it makes thick carbonate sediment. Plus also the development of ooids and micrite forming microscopic calcite crystals. There's so much calcite, so many sources for calcite in warm tropical oceans, especially when they're shallow, that you get these platforms out here that are really shallow. Look how far away from this island. It's only 0 to 500 feet deep. How far away that is. Okay, because of the vast quantity of carbonate material that's piled up there at the bottom. Okay, so that's how you get a carbonate platform. And the stromatolites, those tend to form in my tidal flats. Okay, all of these leave fossil remnants that make sedimentary structures and can provide data for interpretation. Any questions about marine sedimentary structures? No? Obviously, these aren't all of them. I'm just hitting the more relevant, important ones that you'll need to know. All right. Shall we move on to terrestrial structures? We shall. All right. So let's start off by talking about soil. You're familiar with this. Okay, soil is a combination of 4 things. Water, air, humus, not hummus, humus, and mineral content. You need all 4 of them. Without one of those, you do not have soil. Take the dirt on Mars, for example. The dirt on Mars has mineral content and air. There's no water, there's no organic content. It will never grow anything without us adding more stuff to it. Have you guys ever seen The Martian with Matt Damon? Yeah? Gosh, has it already been 10 years since that movie came out? I think it's been 10 years. I think it came out in 2015 or so. That's crazy. But you know what he did? You know how he grew potatoes? He pulled Martian soil into his habitat and then fertilized it with his own poop. He didn't have a choice. He had to add organic content, right? Now, it's not sustainable in the long run for genetic reasons, like it really messes with your body's health and the stability of your genes if you eat plants fertilized with your own waste, okay? Because your waste is your genetic, like you're casting off these genetic things your body doesn't need, the old cells and whatnot, okay? If you reincorporate that, then you're going to start getting sick after a while, but he had no choice, okay? But he had to add that organic content to his soil, right? Without it, you don't have a soil, you can't grow anything. Now, the balance of those 4 things is dependent on the environment that you're in. Here, we have a much higher mineral content and air ratio than, say, the Amazon rainforest, which has a much higher water and organic content ratio, right? And so we grow different things in different soils as a consequence of that balance. The parent material is the biggest factor in determining your mineral content. The parent material can either come from 2 places, either nearby or not nearby. If it comes from somewhere nearby, we call it a residual soil because it is made with local rock. If it comes from sediment that has been transported from far away, we call it a transported soil because it is not made from local rock. It's made from rock who knows how far away. It could be hundreds, could be thousands of miles away. Okay? As time goes on, my soil, as it's utilized more and more by plant matter, as it becomes more weathered, as it gets even more transported, it's going to resemble the parent material less and less. So even if I have a residual soil made from local rock, if it's an old enough soil, it will be very hard for me to tell chemically that it is made from that original rock, because more and more of its components are getting broken down and utilized by plant matter. These are your soil horizons. Your O horizon is the very top one. That's where your organic matter is currently decomposing. Leaves, sticks, dead squirrels, so on and so forth. Your A horizon, that's your topsoil. So that's going to be where most of your plants grow. That's going to be your largest concentration, your highest concentration of water and air and all of those other things, okay? Your E horizon, this is where things that are not used in the top layer are going to go, okay? It's going to be very clay heavy. And then your B horizon, that's going to be where those clays kind of get compacted down deeper, okay? And it can make that water-resistant layer that we see around here, which is why so much of our water flows over the surface instead of getting soaked into the ground very effectively. And then underneath of that is the material that is actively decomposing, that is actively breaking down. All right, moving on to glacial environments. Remember that a glacier itself is a massive accumulation of a mineral. What's that mineral called? Yes? I was hoping someone else would say it. Baby. Doon, 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 doon. No? You guys know that song? You know the song? Yeah? Yeah? You guys know the song? No, wait, stop. Collaborate and listen. That one, you know? It's a good song. Come on. Vanilla Ice. Classic. It's actually one of my favorite karaoke songs. Okay, so yes, it's made out of ice. It is made out of a mineral, and therefore itself is a sedimentary structure, okay? However, glaciers have the misfortune? I don't know if I could call it misfortune. There is no really fortune here. However, it is a fact that they have a very low melting point compared to other minerals, which means that we don't find ice in sedimentary structures preserved in rock. However, we can find evidence of their passage, evidence of their existence because of the weathering and erosion that they provide. Okay? So where I have a massive 100 million ton mass of ice scraping its way down a valley, it's going to crunch and crush and pulverize all the rocks in its path, and it's going to carve a path through that valley. I can find that valley in the geologic record. It's going to carry materials, including glacial flour, glacial till, and erratics downhill and deposit them somewhere. And those can get preserved in other sediments, and I can see that as a sedimentary structure. So the evidence of the existence of these glaciers can be preserved, though not the glaciers themselves. Okay? So what sort of glacial landforms do they leave behind? Well, we've got our glacial valleys that they are carving their way through. We've got the cirques, which are essentially the side valleys that feed into the main valleys and add ice to the glacier and sediment to the conveyor belt, right? That's how I described it, moving downhill over time. A fjord is what you get when one of these glacial valleys is flooded. Why would a glacial valley get flooded?
Because the glacier starts to melt.
The glacier's melting, but what does that have to do with it?
It adds all the water
It adds the water to what?
to the valley, so it's losing all.
Yeah, but then it flows back down the valley. It's flowing away from the valley.
Oh, if it like melts and then freezes back up, something.
Nope. You're exploring good ideas here, but let's follow your original idea. Glacier melts. Water flows down valley. Where does it eventually go? Remember your Finding Nemo education, right? All pipes lead to the ocean, right? Well, so do all rivers, okay? All rivers, eventually, are going to lead to the ocean. As you melt enough glaciers, you add enough water to the ocean, what happens to the sea level? It rises. And so my glacial valleys that are close enough to the ocean are going to get flooded as more water is added to them. Do you remember what I told you about how we can track rise and fall of sea level? How do we track rise and fall? Yes. How do we track rise and fall of sea level in sedimentary structures, in the sedimentary record? What clues are there for the rise and fall of sea level? What about the layers? Layers of what? Earlier today, we already discussed that we find one particular size of sediment in deep water. Silts and clays. Good. So the further away from land I get, the smaller my grains get. The closer to land I get, the larger my grains get. So if I wanted to track the rise and fall of sea level, what would I study about my layers of rock? How large the grains are in sequence through time. Youngest on top, oldest on bottom. We have that frame of reference. What do we call that? The law of superposition. So if I'm going from small grains on bottom to large grains on top, knowing that I am staying in the same geographic location, what does that tell me about sea level at that location? Only one of those things is happening. I've said that it's going from smaller on bottom to larger on top. What's happening? Huh? It fell. Sea level fell. Why? Because as time went on from oldest to youngest rock, my grains gradually got bigger, meaning I got closer to shore. Ooh. This is just a taste of the wonder that is Lab 2. Okay? We're going to talk about how you can use those ideas to interpret some rock. Okay? All right. Arêtes are the ridges between your cirques and your valleys. Okay? They're the long and very sharp angled because glaciers are not water. They're not liquid water, I should say. So they are scraping rock off. They are not smoothing rock out. They are scraping rock off the side, and so you're going to end up with a very sharp, angled, dividing line between your valleys there. And the horns are where those arêtes meet up at different points and make a very sharp peak. Yes. All right. Roches montagnaises, we've talked about these. It's that ramp that forms when a glacier pushes itself over a hill that was unfortunately in the way of that glacier's passage. It doesn't completely scrape it flat, at least not at first. Instead, it kind of breaks material off of one side and chunks off the other way and makes this sort of ramp. The sediment that is moved by a glacier, we call this glacial till. You may see it called drift, but I prefer the term till. Okay. This till is broken, shattered pieces of rock, and it is often compressed into a rock that we call a tillite if that sediment is buried and goes through the process of lithification. By studying the composition of tillites, we can know what mountain range nearby that glacier came from, because it's carrying that sediment from that particular location on its way downhill. How does it carry that sediment? Well, that's where these moraines come in. A moraine is the buildup of sediment on the surface of a glacier as it is moving downhill. Your lateral moraines occur on the sides of your glacier, where they are actively scraping material off the side of the valley. Your medial moraines are in the middle of the glacier, and that happens when two lateral moraines meet up as the two glaciers meet up. So the lateral moraines that were on the sides of these two glaciers meet up and become a medial moraine in the middle of the new, larger combined glacier. Okay? And both lateral and medial moraines are conveyor belts for sediment moving downhill until it reaches the point where the glacier is currently melting. That melting point is dumping all the sediment from those moraines in that location, and that makes a wall of sediment, a massive buildup of sediment we call a terminal moraine, because it's happening at the terminus of that glacier, okay, the end of it. Okay, so those are the three types of moraines that are moving sediment downhill, depositing that till, which will get compressed into tillite and give us clues about that glacier. Okay? Any questions about glacial environments and interpreting that? Okay, deserts next. Deserts form all over our planet, but for specific reasons. They don't form in random locations as at first they may appear. There is a pattern to all of this. Okay? Low latitude deserts form as a result of warm, moist air pushing up into the atmosphere at the equator and then getting either shoved north or south of the equator where they cool off. The moisture starts to fall out of the air as it cools off because that air is condensing as it gets colder. Remember convection? Hot stuff rises, cool stuff falls, convection cells, right? That's what we're looking at here. So we have warm, wet air, which is going up, cooling off as it gets shoved north and south. It rains out a lot of that moisture on its way north or south. And so by the time it reaches the land again, about 30 degrees north and south of the equator, it is now cool, dry air. And that's where your low latitude deserts form, about that latitude. Okay. Then we've got interior deserts. These are places that are dry, they're naturally arid as a result of the lack of water nearby. Inside of giant continents, this is very common. This is a part of the reason why the Gobi Desert exists, why the interior Sahara Desert exists, the Simpson and Great Sandy Deserts in Australia. All of those exist because they are on the inside of large continents. That's part of the reason. For the Great Simpson and the Great Sandy and Simpson deserts and Sahara, they also lie along the latitude. So the cool, dry air coming out of the convection cell also helps, but being in the middle of a giant continent is also a factor. Okay. For the Gobi, it's pretty much just the whole inside of a giant continent a factor. Then you've got rain shadow deserts. Who can remind me how a rain shadow desert works? Yes? Mountain blocks the air, but is it blocking the cool air? It's blocking warm air, which also has what? Water. So because it's blocking that warm, moist air, where does the air have to go? It only has one way it can go, up. And as it goes up, what happens to it? But first, something else happens to it. As it goes up, what happens to it? Huh? It's already evaporated. That's why it's in the air. But what happens to this air and the water inside of it as that air goes higher up in the atmosphere? What happens to everything the higher up it goes in the atmosphere? The opposite. It cools off. Have you ever been in an airplane? Did I ask you this? Yes? What happens to your window on the airplane when you go up to high? It gets fogged up, or you see ice crystals forming on it, right? It's because that's because it gets colder the higher up you go, right? The atmosphere is less dense. It doesn't hold as much energy or heat. So as you go up, you get colder. As you get colder, your water precipitates out as rain, which means that only the cool, dry air makes it to the other side of a mountain range. Example here being the Atacama Desert in Chile. Okay? Rainforest on that side, desert on that side, because a wind blows this way, the air goes over the mountain range, rains everything out, the water stays on that side, only the cold air makes it to that side. Okay? And of course, the magic answer to pretty much everything in my class, this all happens because of tectonics. There would not be a mountain range there without tectonics. There would not be a giant continent here without tectonics. There wouldn't be a continent anywhere along the 30th latitude, north or south, if it hadn't been tectonics that put them there. So the development of all of these things ultimately comes down to the vagaries of tectonics. Okay? In a desert, sediment is moved a lot. Weathering is slow. Erosion is constant. And so these processes, these dynamic processes continue, just not at the same pace that you would see if, there was a river running through, moving all the stuff. Air does not have the same viscosity that water does, and therefore cannot push as much energy to move objects. But when we do see the removal of small sediments due to wind, leaving behind only the large sediments, we call this deflation. Deflation leaves the large stuff, carries the small stuff somewhere else. When that large stuff gets left behind, we call that desert pavement. Okay? Usually you'll see this when you're walking through a desert, and you crunch, crunch, crunch. There's just all of a sudden this big field of gravel around you. The sand is not in this particular location. Why? It's all been blown away for one reason or another, leaving only the larger particles that the wind could not move. A couple of other features we see in the desert. A ventifact is an object, usually a rock, that has been sand blasted by the wind to be very smooth on the top. I've seen ventifacts that say if I was looking at a rock shaped like this and only this much of it was above the surface, it's as smooth as an egg up here. But then you pull it up, you're like, oh, that's a really smooth stone. That's cool. You pull it up, and it's just as jagged and chunky and blocky as that, because this has not been blasted by the wind. Only the amount of my rock that was above ground level has been. Everything else completely unweathered by the wind. Okay, that's called a ventifact. And then a yardang is when we see this, a similar sort of effect on a larger geologic structure, except for one thing. It's smoother at the bottom than it is at the top. Why? Yeah. Yes, of course. Why would this geologic structure have more weathering occurring at the bottom than it would at the top? Sorry, what? The wind goes around it? I mean, the wind naturally has to go around it, yes. You're right that there is wind. Wind is the propulsion for the thing, the energy provider for the thing I'm looking for. What is the wind doing besides just moving around this? The wind itself cannot cause weathering. What is, though? What is the wind moving? The loose, it's not really moving rocks, but what do we call the little things that it is moving? The particles, yes. Now, is it moving the larger particles higher or lower? Why? Because they're larger and they require more energy to move, right? It's the bed load that it's pushing along at ground level. The suspended load that they're small enough for the wind to actually pick up, that's the clays and the silts, not really enough to provide any meaningful source of weathering up here. But what's providing the most weathering? The heavier, larger particles down below here. And that's why we see this unequal distribution of weathering, because the larger particles are weathering down here and the smaller ones up here. Thank you. Great. Yes, sure. All right. Now, when that sand gets blown into piles, those piles are called dunes. And these dunes are pushed further and further along in the direction that the wind is forcing them to go. Okay, yeah. And they take this aerodynamic shape. Okay, this sort of ramp with a slope and then a steep slip face on the other side. So the wind pushes sediment up the slope and then it collapses on the other side of the slip face as gravity takes over. And there's this constant push up the slope, collapse this side, push up the slope, collapse this side, push up the slope, collapse this side. Okay? And that's how dunes move. Very slowly, but they do move. That's what happens to the sand. What happens to our silts and clays, the stuff that's carried in the wind, not just along ground level. We call that loess when it is deposited, and it can make it extremely far. This is a fantastic interpretation tool. It can be confusing sometimes, because what if I'm doing a geologic core sample over here off the southern coast of Yucatan, right? And I pull up a layer of sediment that does not match any sediment in South America. Like, okay, I search my database. This is sediment from Africa. How confusing is that? How does that happen? Because loess can get blown all the way across the Atlantic and come over here. So it can be confusing, but it also, once I know what I'm looking at, it also provides me fantastic information about wind patterns at that point in time. So in a million years, if I found that thing, if I went and did that core sample and I found that data, my natural interpretation would be the winds were powerful enough to bring all that over here. That's an environmental interpretation I can make by studying the sedimentology here. Okay? All right. Now, we can also use the loess. People have used deposits of loess because it's very compact, it's very brick-like. They've used them to make houses. There are entire villages carved into deposits of loess. There's this village in Turkey, I can't remember the name, but they actually carved their entire village out of a deposit of volcanic tuff. Volcanic ash, right? Carved an entire city out of it. It's amazing. You should look it up. I really can't remember what the name is called. I don't know. Maybe I'll find a picture of it later. All right. Questions about deserts or sedimentary structures or environmental interpretations with those? All right. Rivers, then. Rivers are bodies of water under the influence of gravity moving downhill. That's what's providing them their energy. They are moving downhill under the influence of gravity. Where are they trying to go? All rivers lead to the ocean. Bingo. They are trying to get to the ocean. Once they reach the ocean, gravity can't force that water to go anywhere else. So, there are a couple of different types of rivers, though. I showed you this model before when I was teaching you about meandering rivers. Meandering rivers are the ones that kind of wander along, picking their way this way and that way. Not only does water go downhill, it also chooses the path of least resistance, right? So as my river is wandering its way downhill, it's going to spread out and move and go wherever the path of least resistance is. Occasionally, once it spreads far enough from the central course of the river, it's going to take more energy to go out there than it would be to just snap back closer to the middle. And therefore, it's going to choose the path of least resistance, naturally, not an actual choice, right? And snap back over here. Build out again. Too much energy, snaps back here. Too much energy, snaps back here. Okay, and that's how these river valleys are formed, by the winding of these rivers choosing paths of least resistance as gravity is forcing them further and further downhill. As this happens, sediment is removed from the side of the river. We call that a cut bank. And where it is deposited on the inside of my curve, we call that a point bar. And so we have cut bank, point bar. Cut bank, point bar. Removed on this side, added to on that side. Okay? The second type of river we've got, these are called braided rivers. Okay? Because, I mean, for any of you that have ever braided hair, it looks like you've got a dozen different braids splayed out here, like you're going to wind them together. Okay? Braided rivers are higher energy than meandering rivers. Why do you suppose they are higher energy? Under what circumstances would gravity provide more energy to one thing than another?
Going downhill.
They're both going downhill. What's the difference? It's unbalanced? What do you mean? If you want to elaborate, I'm happy to hear it.
Is it what we said?
What was it?
It's steeper.
That's it, okay? It's steeper, all right? The braided river has more energy because it is on a steeper slope, and therefore gravity is providing more energy for acceleration, okay? Think of if I had a ramp here tilted at 1 degree and I put a marble on it, my marble would roll and it would pick up speed, right? Gradually. But if I put a 10-degree slope on it, my marble would roll and pick up acceleration even faster. Same concept. Higher slope, gravity provides more energy for acceleration to happen faster. Okay? So, what does that mean about the particles of sediment that this river can move? Related to the meandering river? No. Cat noises don't count. Are the particles in my meandering stream going to be larger or smaller than the ones in my braided stream? Why? Particle size is directly correlated to?
Oh, because the braided is hitting everywhere. Or like the rocks are hitting everywhere in the water.
We're not there yet.
If it's low energy, it's going to be small particles.
Exactly, it has to do with the energy. Larger energy, larger particles my water can carry. And so because my braided streams have higher energy, they can carry larger particles. So you'll often see these little islands between each one of these streams here is made out of larger particles, cobbles, boulders even, right? This often will have so much energy in the water that it can carry much, much larger particles than meandering streams can. Okay, so if I come across a layer of sedimentary rock with a deposit of big chunky rocks that have been smoothed out because of weathering, just like Jackson was pointing at there. Okay, so they're obviously rounded. They're obviously been moved by water, but it's a repeating sequence of larger rocks. That's a pretty good indicator to me. I'm looking at a braided stream instead of a meandering stream. Okay, and that tells me the steepness of my slope. And the composition of my minerals or of my rocks there can tell me a lot about the environment that it formed in. Lakes. We haven't talked a whole lot about lakes yet in my classes. Well, we're going to talk about lakes now. Rivers often empty into lakes. A lake will typically form where there is some layer of rock beneath this area that water cannot pass through, and so water kind of pools on it. Or you have reached the local water table. That's the more common reason. Remember, a water table is the invisible line, right? It's not an actual line we draw underground, but it is the line at which the plane underground at which the ground is saturated by groundwater. So if my local water table is high enough, then my rivers are going to flow into an area that water can pool in at that water table's depth. And that's how you form a lake. Lakes also usually have outlets. So there's some other river that usually leaves the other side. What we can tell, how we can tell we're looking at a lake is if we can see layers of fine-grained sediment in the middle of an area that is clearly not a marine setting. So why would lakes have fine-grained sediment in them? Remember, fine-grained sediment deposits in what kind of environment? Low energy. Lakes are pretty deep compared to other bodies of water, and they don't have running water like a stream or a river does. It's standing water for the most part. So yeah, I'm going to get larger particles on the outside, medium particles towards the middle, and then in the middle, smaller particles. It'll kind of look like a bullseye because decreasing energy the further inward I go. So you can find very, 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 very thin layers of sediment at the middle of my lake deposits, like that. Here's a penny for scale. Look how thin those layers of sediment are. Now, the thickness or thinness of these layers of sediment is cool because it's actually seasonal. What season do you suppose would provide more sediment to my lake? What season?
Dry season.
Why would the dry season provide more sediment? Gavin, what do you think? Should I back it up a little? Let's back this logic train a little further up the tracks, okay? What is going to deposit sediment in my lake? Water from? The rain's not bringing sediment. The river flowing into my lake is bringing the sediment. So now that we know that the river is bringing the sediment, which season is going to have more water flow to bring that water? And therefore sediment. In what season do we typically get the most rain? Spring. Spring is when we typically get the most rain. Not only that, that's also typically when we have the most ice melt. Okay? As winter is melting, snow and ice up north in higher altitudes is going to melt, feeding water systems. We get more rain at the same time. So in spring, you'll typically see thicker layers of sediment in my lakes. Okay, so what season would have the thinnest layers then? Summer? Sure. Why?
Because it's hot.
It's hot. There's not as much rain. What else?
Winter.
Why winter?
Because it freezes.
Yeah, there's almost no water flow in the winter because it's all frozen. So we can track the seasonality of these layers in these lake deposits by simply making those approximations, those interpretations. Okay? We call these varves, by the way. These layers of sediment, we call those varves. Here's an example of varves right here with thin, dark sediment and thick, light sediment. Thin, dark, thick, light. Thin, dark, thin, light. You can see the seasonality in this varve layering right here from this old lake deposit. Now, occasionally, we're going to find something weird in our lake beds, like this chunk. Can any of you guys tell me what this is just by looking at it, this rock? It's not wood. It's a rock.
That's clay.
No. Okay.
Copper.
We're seeing bands of minerals, like stretched minerals in here. Does that look familiar to anyone from 1403? This is the metamorphic rock gneiss. It's a chunk of gneiss. Notice what it is in. Look at these varves. Varves, 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 varves. Notice that these varves have been kind of pushed down on this rock, and there are varves above the rock. What does this tell you? Interpret this. There are varves below it, which means that the lake was there before. There are varves above it, which means that the lake was there after, depositing on top of it. At some point, for some reason, this chunk of rock fell into the lake, fell to the bottom, pushed down on the layers of sediment beneath it, making that sort of bending shape, and then was deposited on top of and got incorporated into this lake bed. I don't know why that happened. This was millions of years ago. Maybe a dinosaur threw it in. Maybe they were skipping rocks. I don't know, right? Regardless, it happened. Maybe there was a nearby cliff and it fell off. Don't know, but for some reason it happened. Okay? So, with everything that we have learned today, plus a whole lot more that we have discussed in the past, right? We can make interpretations about our world today and our world in the past by comparing what we know about both. I know what a sand dune looks like right now. I know what it looks like in cross-section. I know how it forms. I know how it moves. I know how they pile on top of each other. Because I know that, I can look at this, the cross-bedding of all this sand piled on top of itself in the exact same way that my dunes do now. And I would know that what I'm looking at here is an old dune system. This is an old desert. This is a desert now, but the physics that are influencing this now made this a long, long time ago. This is the principle of uniformitarianism. The same processes that occur today happen in the past. The caveat there being what? What else? Physical, chemical, and biological laws that operate today also operated in the geologic past and will operate in the geologic future. And what else? Maps? What do you mean? And everywhere else. What are we looking at in this picture? What is this?
Oh, it's an old lake bed.
That's the moon. The moon.
What is this shape? What does it make you think of? A lake?
Yeah.
Does that look like a lake, or does it look like something that would be in a lake?
Looks like a lake bed.
Looks like the lake dried up. Shit, man.
What is this? What is this? It's a delta. This is a river delta emptying into a large body of water. Look at that shape, my friends. And then look at that. What is this? This is a delta from a river emptying into a larger body of water. This is a picture from Mars. This is a picture from Mars.
I said Mars.
This is a delta 2 billion years gone. This is a river that used to flow into a ginormous lake on the surface of Mars. Look at this, this asteroid crater. This delta has been dead so long that this asteroid crater formed on top of it. Something went kapoof right there long after this thing dried up. Okay? As a matter of fact, right here, I believe, is where the Perseverance rover has been making its many-year journey collecting geologic samples to look for fossils. And those samples are going to come back to Earth in 2035. And that'll hopefully give us our final answer of whether or not life ever existed on Mars. If life ever existed on Mars, it's going to be here where there was flowing fresh water into a lake. Okay? This is the most promising location that we can see on the entire surface of Mars where life could have existed. If it was anywhere, it's going to have existed there. So, well, hey, it's right. We'll find out. We will find out. There's some very interesting dilemmas for why life could have or could not have existed on Mars. Okay? You guys want to hear an interesting one? Should we go off on a tangent? It's the end of the class. All that's left at this point is to tell you about the lab. So I'll go off on a tangent for a minute, okay? Have I already talked to you about phosphorus? About the relationship between phosphorus and tectonics?
Oh,
I think it was in lecture one.
It wouldn't. It was not part of the schedule for lecture one. If it was, I don't remember talking about it. I'll just say it again, okay? Phosphorus is required for life. How many of you have taken fundamental biology? Do you know what ATP is? Yeah. It has to do with energy, yeah.
I know the third word is phosphorus.
ATP, yeah, sure. Adenine triphosphate. Adenine being one of the essential amino acids required in the creation of our DNA. Okay? Adenine triphosphate is the mechanism by which all living things on our planet store energy. Okay? Without it, can't store energy, can't exist, can't live. Life as we know it does not exist. Now, that requires the element phosphorus. Phosphorus is one of the rarest elements on our planet. And yet there's enough of it for all of this life to exist. Plants, bugs, insects, bacteria, us. Okay? Everything in the ocean too. Fish, seaweed, my goodness, plankton, right? Everything on Earth uses ATP. Now, how has life existed this long and this many things on Earth existed all sharing this one, this one tiny, minute amount of phosphorus on our planet? No, recycling. Recycling. When stuff dies, it gets incorporated into the crust in the ocean or on the land. That crust eventually gets shoved down into the mantle. It gets melted. That melted stuff pushes its way back up to the surface and gets expelled through a volcano, including the phosphorus. That phosphorus makes its way back onto the ecosystem and can be used by life again. Phosphorus recycling is the only reason why we have been able to have this long history of life here. As we understand it, Mars has no tectonics, and as far as we can tell, never did. It's a distinct possibility that Earth only has tectonics because of the collision with that other planet 4 billion years ago. So, if tectonics is the only reason why phosphorus has been able to recycle itself through our Earth system, and phosphorus is required for life, the next logical conclusion is that on a world where phosphorus cannot be recycled by tectonics, stuff lives, stuff dies, it gets buried, it stays buried. It never makes its way back up to the surface. It can never be reused. This puts a time constraint on the existence of life on such a planet. There comes a point in time where there is so little phosphorus on the surface, life cannot renew itself. ATP cannot be made. Energy cannot be processed or stored. Life dies out. So this begs the question, if Mars's atmosphere had not evaporated because its core had cooled off and its magnetic field dissipated, if its atmosphere had not been blown away, if its water had not been evaporated into space, would life even still be there right now? Yeah.
I don't know if this is how it works, but wouldn't the under the Earth, wouldn't that cool off so the tectonics would stop moving around?
We would still see the suture marks between tectonic plates, though. Well, there wouldn't be movement necessarily, but there should still be obvious tectonic boundaries like what we can clearly see here on Earth. Even with how dynamic our surface is, we can still clearly see our tectonic plate boundaries. We cannot see those on Mars. As far as we can tell, it never had tectonics. It had volcanism, obviously.
My head hurts.
All right. Isn't that interesting, though? Life on Mars may have been doomed already without what happened to its core. Okay? Just an interesting tangent there. All right, let's talk about your lab before I run out of memory on my recording here.
Everybody else can
Remy, should I relocate you for your safety? He's thinking about it. Let's talk about lab real quick, and then you can go, okay? I'm going to introduce you to how Lab 2 works. All right, so this is a lab about stratigraphy. Remember, stratigraphy is the study of the relationship, I should say, between layers of rock. The sequence of rocks tells us a lot about, and everything about when you think about it really, the timeline of how events progressed, okay? So, the layers you can see in these rocks, that is stratigraphy. The sequence of those layers is how we piece together the past. This is from the book Cliffs, by the way. Okay, so we've already talked about all that. We talked about all these. We talked about grain size and everything. Okay, we've talked about a lot of this. Now, there are a few exceptions to the rule of the law of superposition. Remember, the law of superposition states that everything on the bottom is older and everything on the top is younger. But what if I have layers of sedimentary rock following that law and then some igneous Pluton decides to be rude and cut right through them? I know, the gall. Right here, sedimentary rock, igneous rock, sedimentary rock. Which one's younger? Is it old? Is it oldest, older, youngest? No, it can't be. This rock must have been here to begin with for that igneous rock to cut through, which means that in this case, my youngest rock is the igneous rock. Here, I have sedimentary rock, vertical dikes running perpendicular to them. Which one's younger? The dikes. They must be the youngest because that other rock must have been there in the first place for that dike to cut through. You see what I'm saying here? It's not always as cut and dry as oldest, older, younger, youngest. You have to keep in mind the features that can break that rule. Logic your way through understanding them. Okay? So this is your lab. You're going to get something that looks like this. Okay? There are 3 different parts to your stratigraphic column. Your grain size, your lithology, and your description. I am going to give you 2 out of the 3 for every section of this lab, and it's your job to fill in the other section, okay? So, for example, if I were to give you these 2, the grain size and the lithology symbols, you would need to interpret that to give me the description. If I gave you the description and the grain size, you would need to give me the lithology. So on and so forth. Okay? So this right here, this is going to be your best friend for this lab. Okay? This is your key for interpreting symbols and giving a description, or seeing a description and finding the symbol that you need to fill in. All right? So you are getting a chart just like this, but I have already pre-filled in some of the sections, and you are filling in the blanks that I did not give you, be that description, lithology, or grain size. You can use this slide to find the lithology and interpret for descriptions. The grain size is going to be determined by the description. So for example, if I were to say that I put right here, medium, we good? Medium grain sandstone, okay? You would go up here and you'd be like, okay, well, there's the M, that stands for medium, by the way, okay? So it's clay silt, very fine, medium, coarse, very coarse, and then gravel, 4 millimeters and 64 millimeters. You would look for the M, okay, down here is the medium grain sandstone, draw a line right there, corresponding with the M up there standing for medium grain size, okay? And then you would just draw that same line back and forth, zigzagging it back and forth according to whatever the grain size is for the description and lithology. Okay? For things like limestone that don't actually have a grain, they are crystallized, you can just pull your line all the way over to clay to stand for microscopic crystals. Okay? Questions? Okay. I don't have any hard copies of these right now, but if you guys want to start working on this lab today, I can run upstairs and print off a bunch of these so you can start working on them. Do you want me to do that?
What's your own? That's all just that.
This one sheet, yeah.
Well, that's why. They opened it and I saw it.
You haven't even started it yet, brother.
I opened the assignment like earlier, so I was getting it, and I only saw like maybe 10 questions.
For lab 2?
Yeah, like just 10 of those things.
Oh, the rows?
Yeah.
Yeah, this should be around there. Okay, I'm going to end the recording here. Online students, unfortunately, you'll either have to do this digitally or print this off yourself. I obviously can't provide you a printed copy, but you can either print it off, or I have had students that do this whole thing digitally. It might take a little extra time, but you won't need access to a printer. As always, if you have any questions, feel free to email me.